Imagine being stranded in the middle of the Pacific Ocean. No land in any direction, just water stretching to every horizon. Now multiply that loneliness by 1 billion. That is what it would feel like to exist inside the Boötes void. A region of space so empty, so staggeringly vast, that if you placed an entire galaxy at its center and looked outward, you would see almost nothing for hundreds of millions of light years in every direction. No stars, no galaxies, no glowing nebulae, just darkness. Cold, indifferent, incomprehensible darkness. The universe is supposed to be woven together, threaded with billions of galaxies arranged in a grand cosmic web. Yet here sits a hole in that web, so enormous that our best models of how the universe evolves struggle to explain how it got there. Astronomers did not predict it. The math did not expect it. And when the data first came back from the telescopes, the team that found it assumed their equipment was broken. It was not broken. The universe simply had a secret it had been keeping for 13 billion years. To understand why a patch of empty sky unsettled the entire field of cosmology, you first need to understand what astronomers thought the universe looked like before they found it. And to do that, you need to go back to a time when our picture of the cosmos was embarrassingly incomplete. For most of human history, we had no idea how galaxies were distributed in 3 dimensions. We could look up, we could photograph the sky, we could catalog millions of points of light and sort them into constellations and clusters. But all of that was flat. It was like looking at a photograph of a forest and trying to figure out which trees were in the front and which were a mile behind. The sky gave us angles, but it refused to give us depth. Think about it this way. You walk outside on a clear night. You see a bright star near the horizon. You see a faint one overhead. Is the faint one farther away, or is it just dimmer? You cannot tell. Not from brightness alone, not from position alone. You need a ruler. You need something that tells you how far away each object actually is. For nearby stars, astronomers had a method. Parallax. As the Earth orbits the Sun, the closest stars appear to shift slightly against the background of more distant ones. You can measure that shift and use basic geometry to calculate distance. This works beautifully for stars within a few thousand light years. But galaxies are millions, hundreds of millions, billions of light years away. Parallax is useless at those distances. The shift is so tiny it vanishes into the noise. For most of the 20th century, we could see galaxies scattered across the sky like paint splatter on a ceiling, but we had almost no way to know how far away most of them were or how they were arranged in 3-dimensional space. That changed because of a phenomenon called redshift. You have almost certainly heard of the Doppler effect, even if you do not know the name. When an ambulance drives toward you, the siren sounds higher pitched. When it drives away, the pitch drops. This is because the sound waves get compressed as the source approaches and stretched as it recedes. Light behaves the same way. When a galaxy is moving away from us, the light waves it emits get stretched. Longer wavelengths of visible light look redder, so astronomers call this stretching a redshift. The greater the redshift, the faster the galaxy is moving away. Now here is the critical piece. In 1929, Edwin Hubble demonstrated something extraordinary. He showed that the farther a galaxy is from us, the faster it is receding. This is not because galaxies are flying apart like shrapnel from an explosion. It is because the fabric of space itself is expanding. Every point in the universe is moving away from every other point, and the expansion rate is roughly proportional to distance. This relationship, known as the Hubble-Lemaitre law, turned redshift into a cosmic ruler. If you measure how much the light from a galaxy has been stretched, you can calculate how fast it is receding, and from that recession speed, you can estimate its distance. Suddenly, astronomers had the tool they had been dreaming about for decades. They could take the spectrum of a galaxy, measure its redshift, and pin it to a position in 3-dimensional space. They could build a map. But measuring a spectrum takes time. You cannot just point a camera at the sky and snap a picture. You need to capture the light from a single galaxy, spread it out into its component wavelengths using a spectrograph, and then carefully measure the positions of specific spectral lines. In the 1970s and early 1980s, this was painstaking work. Each galaxy required its own dedicated observation. You could not do thousands in a night. You could do a handful, maybe a few dozen if conditions were perfect and the telescope schedule was generous. This meant that the first three-dimensional maps of the universe were sparse. They were built galaxy by galaxy, like placing individual pins on a globe. Early surveys mapped a few hundred galaxies at a time. They were not designed to reveal the grand architecture of the cosmos. They were designed to answer simpler questions. How are galaxies clustered? Do they clump together or spread evenly? Is there a pattern to the distribution? It was in this era of early cartography that a small team stumbled onto something that should not have been there. In 1981, Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Shectman were conducting a redshift survey. Their method was straightforward but effective. They selected several small patches of sky in different directions and measured the redshifts of all the bright galaxies they could find within those patches. The idea was to sample the universe in multiple directions and compare the distributions. If galaxies were spread roughly evenly, the samples would look similar. If there were large-scale structures, clusters, or walls of galaxies, those would show up as peaks in the data. The survey was modest in scope. It was not a monumental project designed to map the entire observable universe. It was a careful, systematic probe. A set of boreholes drilled into the cosmic landscape to see what lay beneath the surface. One of the patches they chose was in the direction of the constellation Boötes. Boötes is a northern sky constellation, visible from most of the northern hemisphere, best known for the bright orange star Arcturus. There was nothing special about this patch. It was simply one of several fields they had selected for their survey. They pointed their telescope, collected the light, measured the redshifts, and plotted the results. When the data came back, something was wrong. In every other direction they had sampled, the distribution of galaxies looked roughly as expected. There were clumps. There were gaps. The galaxies were not perfectly uniform, but they formed a recognizable scatter, a texture. You could look at the distribution and see a pattern that matched your intuition about how matter should be arranged. Dense regions here, thinner regions there, a cosmic fabric with some variation. But in the direction of Boötes, there was a hole, not a small gap, not a modest underdensity, a chasm. The data showed a vast region of space, centered at a redshift corresponding to a distance of roughly 700 million light-years from Earth, where there were almost no galaxies at all. The team looked at their measurements and saw what amounted to an enormous empty bubble in the three-dimensional distribution of matter. The immediate assumption was that something had gone wrong. In science, when your data shows something that makes no sense, your first instinct is not to rewrite the textbooks. Your first instinct is to check the cables. Maybe the spectrograph had malfunctioned. Maybe there was a calibration error. Maybe clouds had interfered with the observations. Maybe they had simply gotten unlucky and sampled a small gap that would fill in with more data. They checked. They rechecked. They looked for systematic errors. They re-examined the photographic plates. They considered whether dust in our own galaxy might be blocking the light from distant galaxies in that direction. Galactic dust is a real problem. It can absorb and scatter light, making certain patches of sky appear emptier than they actually are. Astronomers even have a name for the worst of these obscured regions. They call them the zone of avoidance, the band around the Milky Way's plane where dust is so thick it blocks our view of extragalactic objects almost completely. But the Boötes field was not in the zone of avoidance. It was well away from the galactic plane. The dust in that direction was minimal. There was no obvious obstruction that could account for the absence of galaxies. The void was not a shadow cast by our own galaxy. It appeared to be a genuine emptiness in the distribution of matter at cosmological distances. Kirshner and his colleagues published their findings in the Astrophysical journal Letters in 1981. Their paper was careful and measured. They did not claim to have discovered the largest structure in the universe. They reported what they had found, noted that the void had an approximate diameter of at least 100 million light-years based on their initial data, and acknowledged that the true extent was uncertain because their survey covered only a limited region. But the implication was clear. There was something very unusual about that part of the sky. The reaction from the astronomical community was a mix of curiosity and skepticism. This was, after all, an era when large-scale redshift surveys were still in their infancy. The maps were rough. The samples were thin. It was entirely possible that a larger, more comprehensive survey would fill in the gap with galaxies that the original team had simply missed. Some astronomers suggested that the void might shrink once more data was collected. Others proposed that it might be a statistical fluctuation, a random underdensity that happened to fall within the team's survey field. These were reasonable objections. In science, you do not overturn your understanding of the cosmos based on a single survey of a few hundred galaxies. You wait for confirmation. Confirmation came, and it made things worse. Throughout the 1980s, redshift surveys grew larger and more ambitious. The Center for Astrophysics, a joint institution of Harvard University and the Smithsonian, was conducting its own large-scale survey, known as the CFA Redshift Survey. The first phase, completed in the early 1980s, mapped the positions of several thousand galaxies in the northern sky. The second phase, which extended through the late 80s and into the early 1990s, was far more comprehensive. It covered a wider area and went deeper. As the CFA data accumulated, the cosmic cartography started revealing structures that no one had imagined. In 1989, Margaret Geller and John Huchra published a map from the second CFA survey that became one of the most famous images in the history of astronomy. It showed a slice of the universe, a thin wedge of three-dimensional space, and it was stunning. The galaxies were not scattered randomly. They were arranged in vast sheets and filaments, long chains of clusters that connected like bridges across enormous empty regions. One of the most dramatic features was a structure they called the Great Wall, a sheet of galaxies stretching at least 500 million light-years across the sky. It was the largest coherent structure ever observed in the universe at that time. But the Great Wall was only half the story. The other half was what the Great Wall was bordering. The CFA maps also confirmed in vivid detail the existence of enormous voids, regions where the galaxy density dropped to a fraction of the cosmic average. The universe was not a smooth distribution of matter. It was a foam, a cosmic sponge, dense walls and filaments surrounding vast empty bubbles. And the Boötes void was the biggest bubble anyone had found. As more surveys mapped the region around Boötes with greater precision, the void did not shrink. It grew. Deeper observations revealed that the emptiness extended even further than Kirshner's original estimate. The refined measurements placed its diameter at approximately 250 million light-years, with some analyses suggesting it could be closer to 330 million light-years, depending on exactly where you draw the boundary. It was roughly spherical in shape, though not perfectly so. Its edges were not sharp walls, but gradual transitions where the galaxy density slowly climbed back toward the cosmic average. Let me give you a sense of what that means. The Milky Way galaxy, our home, is roughly 100,000 light-years across. The Boötes void could swallow more than 3,000 Milky Ways lined up side by side, and still have room. The distance from our galaxy to Andromeda, our nearest large neighbor, is about 2.5 million light-years. You could fit the Milky Way-Andromeda gap inside the Boötes void over 100 times. The entire local group, the collection of more than 80 galaxies gravitationally bound to each other, including the Milky Way, Andromeda, and the Triangulum galaxy, would be a speck of dust floating in this emptiness. And inside this vast expanse, Almost nothing. Subsequent observations found that the Boötes void is not absolutely empty. There are galaxies inside it, but the number is shockingly small. Surveys have identified roughly 60 galaxies scattered throughout the interior. 60. In a volume of space where, given the average density of galaxies in the universe, you would expect to find on the order of 2,000 or more. The interior of the Boötes void is not a vacuum. It is not a region of zero matter. But it is so profoundly underdense that it represents one of the starkest departures from the cosmic average anywhere in the observable universe. Imagine a city. A city like London or Tokyo, millions of people packed into a dense urban grid. Streets full of traffic, buildings in every direction. Now, imagine you find a zone in the middle of that city. A zone the size of a county where there are only a few dozen scattered houses. No roads, no infrastructure, no crowds, just a handful of lonely structures separated by miles of empty land. That is what the Boötes void looks like against the backdrop of the cosmic web. The discovery of the void, and its confirmation by increasingly powerful surveys, forced astronomers to confront a question that had been lurking at the edges of cosmology for years. We knew the universe had structure. We knew there were clusters and walls and filaments, but we had assumed that the variations were modest. We had assumed that on large enough scales, the universe was homogeneous, smooth, even. The cosmological principle, one of the foundational assumptions of modern cosmology, states that on sufficiently large scales, the universe looks the same in every direction and from every location. No special places, no special voids, no special walls, just a uniform fabric. The Boötes void did not violate the cosmological principle outright. The principle was always understood as a statistical statement, an average. Small-scale variations were expected. But the void was not small. It was enormous, and its existence raised an uncomfortable question. How large does a structure have to be before it starts to challenge the assumption of homogeneity? Where is the line between a normal fluctuation and an anomaly that our models cannot explain? The surveys that confirmed the Boötes void were not the end of the story. They were the beginning. In the early 2000s, the Sloan Digital Sky Survey began operation. It was the most ambitious redshift survey ever attempted. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, the survey measured the spectra of millions of galaxies across a vast swath of the sky. It produced three-dimensional maps of the universe with a level of detail that dwarfed everything that had come before. The Sloan data confirmed the existence of the Boötes void and placed it within the broader context of cosmic large-scale structure. The survey revealed hundreds of voids scattered throughout the observable universe. Voids of varying sizes, from modest pockets a few tens of millions of light years across to sprawling emptinesses exceeding 100 million light years. The cosmic web was mapped with unprecedented clarity. Filaments, walls, clusters, and voids formed an intricate, three-dimensional tapestry that looked remarkably like the output of computer simulations based on the standard cosmological model. But even in this detailed map, even surrounded by hundreds of other voids, the Boötes void stood out. It was the largest, the emptiest, the most extreme. It sat in the data like a hole in a tapestry. Not a tear caused by damage, but a region where the threads were simply never woven. And that is what unsettled people. A void is not unusual. The universe is full of them. They are a natural consequence of the gravitational evolution of matter. But a void of this size, with this degree of emptiness, sits at the far edge of what the standard model predicts should exist. It is not impossible, but it is improbable. And in science, when something improbable stares you in the face, you have two choices. You can shrug and call it a statistical fluke, or you can take it seriously and ask whether your model is missing something. The discovery of the Boötes void was not a single dramatic moment. It was a slow revelation, a gradual dawning of recognition that something extraordinary was hiding in an ordinary patch of sky. It began with a team of 4 astronomers conducting a routine survey and finding an absence where they expected presence. It grew as larger and more powerful surveys confirmed that the absence was real, persistent, and far bigger than anyone had initially guessed. And it matured into a genuine scientific puzzle when the community realized that this emptiness was not just large. It was anomalously large, uncomfortably large, large enough to make the theorists pause and the observers keep looking, hoping to find an explanation that would let everyone sleep a little easier. They are still looking. The Boötes void sits out there, roughly 700 million light-years from Earth, a sphere of almost nothing embedded in a universe of almost everything. It does not glow, it does not pulse, it does not send signals, it simply exists in its absence. And that absence, that quiet, patient emptiness, has been asking the same question for over 4 decades. How did you get here? And why are you so impossibly big? Those are the questions that haunt cosmology. And the answers take us deep into the machinery of the cosmos itself, into the physics of how the universe builds its largest structures, and into the unsettling realization that the emptiest place we have ever found may be telling us something profound about the forces that shaped everything. But first, we need to feel the size, not as a number, not as a statistic, as a physical reality that sits in your chest and refuses to leave. We know the Boötes void is big. We have used that word several times already. Big, enormous, vast. But those words are worthless. They are placeholders. They are the verbal equivalent of shrugging. Because the human brain did not evolve to comprehend distances on this scale. We evolved to judge the distance between a tree and a lion. We evolved to estimate whether we could throw a rock far enough to hit a rabbit. Our spatial intuition maxes out at a few miles. Maybe a few hundred miles if you have flown in a plane and stared out the window. Beyond that, the numbers become abstract. They become sounds. They stop carrying emotional weight. So before we go any further, before we talk about the physics of void formation or the implications for cosmology, we need to fix this problem. We need to make the size of the Boötes void feel real. Not just intellectually, physically, in your bones. We need to build a ladder, and we are going to climb it rung by rung, starting from something that you can hold in your hands and ending at a scale so large it will make the entire observable universe feel like a crowded room with one enormous missing piece of furniture. Let us begin with something familiar. The Earth. You live on it. You have a rough sense of its size. If you got in a car and drove around the equator without stopping at highway speed, it would take you about 17 days. The circumference of the Earth is roughly 40,000 kilometers, or about 25,000 miles. That is a number you can almost feel. You have driven long distances. You know what 1,000 miles feels like. 25 trips of 1,000 miles each gets you around the planet. That is your baseline. Hold it in your mind. Now, leave the Earth. The Moon orbits at an average distance of about 384,000 kilometers. That is roughly 30 Earths lined up side by side. If you could drive to the Moon at highway speed, it would take you about 5 months. Far, but not unimaginable. Astronauts made the trip in about 3 days using rockets. The Moon is close. It is our neighbor. You can see it from your window. Now jump to the Sun. The distance from the Earth to the Sun is about 150 million kilometers. Astronomers call this one astronomical unit. It is the yardstick of the solar system. Light covers this distance in about 8 minutes. If you tried to drive it, assuming you had a very long road, it would take you roughly 170 years. You would not make it. Your grandchildren would not make it. But in cosmic terms, this distance is nothing. It is a rounding error, a speck of dust on the map. Let us go further. The outer boundary of the solar system is hard to define precisely. But if we use the Oort cloud as our marker, the shell of icy debris that surrounds the Sun at extreme distances. Then the solar system extends roughly 1 to 2 light years from the Sun in every direction. A light year is the distance light travels in 1 year, about 9.5 trillion kilometers. Already the numbers are becoming meaningless. Trillions of kilometers. What does that even feel like? It feels like nothing. It is just a number. So let us use light years as our new unit and forget about kilometers entirely. The nearest star to our Sun is Proxima Centauri. It is about 4.2 light years away. If you fired a bullet from a rifle and aimed it at Proxima Centauri, that bullet would take roughly 1,300,000 years to arrive. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of about 692,000 kilometers per hour. Even at that speed, it would take more than 6,000 years to reach the nearest star. 6,000 years ago, the Sumerians were inventing writing. That is the timescale we're talking about just to reach the house next door on the cosmic street. Now zoom out. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. It is shaped like a flat spiral disk with a bright bulge at the center and sweeping arms curving outward. The disk is roughly 100,000 light years in diameter and about 1,000 light years thick. If you could fly across the entire Milky Way at the speed of light, the fastest speed the universe permits, it would take you 100,000 years. 100,000 years at the maximum velocity allowed by the laws of physics just to cross from one edge to the other of one single galaxy. Hold that number. 100,000 light years. That is the size of the thing we call home. Now let us introduce the neighbors. The Milky Way is not alone. It belongs to a small collection of galaxies called the Local Group. This group contains more than 50 galaxies, with recent surveys pushing the count above 80 and possibly beyond 100 when the faintest dwarf galaxies are included. The two heavyweights are the Milky Way and the Andromeda Galaxy. Andromeda is about 2.5 million light years away. You can actually see it with your naked eye on a dark night. It appears as a faint smudge in the constellation Andromeda. That smudge contains roughly 1 trillion stars, and the light you are seeing left at 2.5 million. Years ago, back when our ancestors were just beginning to walk upright on the African savanna. The Local Group as a whole spans roughly 10 million light years. This is our cosmic backyard, our village. Everything within this volume is gravitationally bound to us. These galaxies are not flying apart with the expansion of the universe. They are held together by mutual gravity, orbiting each other in a slow gravitational dance that will continue for billions of years. Now, let us step beyond the village. The Local Group sits on the outskirts of a much larger structure called the Virgo supercluster. A supercluster is a vast collection of galaxy groups and clusters, connected by filaments and bridges of galaxies, spanning hundreds of millions of light years. The Virgo supercluster contains roughly 100 galaxy groups and clusters, including the massive Virgo cluster at its heart, which alone contains more than 1,000 galaxies. The entire supercluster stretches roughly 100 to 150 million light years across, depending on where you draw the boundary, and in 2014, astronomers redefined our cosmic address even further. A team led by Brent Tully published a study identifying an even larger structure that they called Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a supercluster of superclusters. It contains the Virgo supercluster, the Hydra Centaurus supercluster, and several other enormous collections of galaxies. The total span of Laniakea is approximately 500 million light years, and it contains roughly 100,000 large galaxies and an estimated total mass of 100 million billion suns. 520 million light years across. That is the scale of the superstructure that we are part of. It took the combined effort of decades of redshift surveys, computer modeling, and gravitational mapping to even identify it. It is so large that light from one end has not had time to reach the other end since the supercluster began to form. Now, with all of that in your mind, with the ladder fully built from the surface of the Earth to the scale of Laniakea, let us look at the Boötes void. The Boötes void has an approximate diameter of 330 million light-years. Let that register. 330 million light-years. That is more than 3,000 Milky Way diameters. It is over 130 times the distance from the Milky Way to Andromeda. It is roughly 3 times the diameter of the Virgo supercluster. It is more than 60% the diameter of Laniakea itself. Imagine the entire Virgo supercluster, all 100 galaxy groups, all the thousands of galaxies, all the trillions of stars, all the planets and gas clouds and dark matter halos that make up our cosmic neighborhood. Now imagine placing that entire supercluster inside the Boötes void. It would fit, comfortably. You could fit several of them inside the void and still have empty space left over. The Boötes void could swallow our entire supercluster, the way your living room could swallow a marble. And inside this marble-swallowing emptiness, there are roughly 60 galaxies. 60. To grasp how barren that is, consider what the same volume of space would contain if it had the average density of the universe. Estimates vary depending on which survey data you use and how you define the boundary of the void. But a reasonable calculation suggests that a sphere 330 million light-years in diameter, located in a region with average galaxy density, would contain somewhere between 2,000 and 10,000 galaxies. The range depends on how you count dwarf galaxies versus large spirals and ellipticals, and on the completeness of the survey. But even at the conservative end, 2,000, the Boötes void contains only about 3% of the expected number. It is not slightly empty. It is catastrophically empty. Let us try a different analogy. Imagine the state of Texas, about 270,000 square miles of land. Now imagine that across the entire state, there are only 60 houses. No towns, no cities, no villages. Just 60 isolated structures scattered across an area larger than France. The nearest house to you might be 50 miles away, or 100. Or 200. You could drive for hours and see nothing but flat, empty ground. That is the galaxy distribution inside the Boötes void. Now consider what this emptiness means for an observer inside it. This is a thought experiment that astronomers have discussed, and it is one of the most haunting images in all of cosmology. Imagine you live on a planet inside the Boötes void, not near the edge, where you might still catch a glimpse of the denser regions beyond, but deep in the interior. At the center, you develop astronomy. You build telescopes. You look up at your night sky. What do you see? If you live in the Milky Way, your night sky is magnificent. On a clear dark night, you can see thousands of individual stars with your naked eye. You can see the bright band of the Milky Way arcing overhead, the combined glow of billions of distant stars in the galactic disk. With a small telescope, you can see neighboring galaxies. With a large one, you can see thousands of them. The universe feels full, crowded even. But inside the Boötes void, your sky would be desolate. Your own galaxy would still be there. You would still see your local stars. But beyond your galaxy, almost nothing. The nearest large cluster of galaxies might be 100 million light-years away or more. With the kinds of telescopes that existed on Earth in the 19th century, you might not detect a single external galaxy. The sky beyond your own stellar neighborhood would be black and featureless. You might reasonably conclude that your galaxy was the only one in existence. You might develop a cosmology that said the universe was your galaxy and nothing else. An island of light in an infinite sea of darkness. It would take extraordinarily powerful instruments, far beyond anything early astronomy could produce, to detect the faint smudges of light from the distant galaxies beyond the void's edge. And even then, those galaxies would appear abnormally sparse compared to what we see from our position in the relatively dense cosmic web. This thought experiment is not just poetic. It illustrates a genuine scientific point. The Boötes void is so large and so empty that it would fundamentally alter the observational experience of any civilization living inside it. It would shape their entire understanding of the cosmos. It would warp their intuition about how much stuff the universe contains. They would have no way of knowing, without extraordinary effort, that the rest of the universe was teeming with galaxies. Their local sample would mislead them about the nature of reality. We should pause on this, because in a way, this thought experiment applies to us as well. We assume that our view of the universe is representative. We assume that the density of galaxies we see from our position in the Virgo supercluster is typical. But the existence of the Boötes void reminds us that position matters. Where you sit in the cosmic web determines what you see, and what you see determines what you believe about the universe. Our cosmology is built on the assumption that the universe is homogeneous on large scales. The Boötes void is one of the biggest tests of that assumption. Let us return to the galaxies that are inside the void, because their arrangement is significant. When astronomers looked carefully at the positions of the roughly 60 known galaxies within the Boötes void, they noticed something interesting. The galaxies are not randomly scattered like salt thrown on a table. They appear to be loosely arranged along a thin, tube-like filament that runs through the interior of the void. This filament, sometimes described as a tenuous chain of galaxies, threads through the emptiness like a single strand of cobweb stretched across a dark room. This structure is faint, it is fragile, it contains far fewer galaxies than the robust filaments that make up the dense walls of the cosmic web outside the void. But it is there. And its presence tells a story. It suggests that the Boötes void is not a pristine, untouched bubble of primordial emptiness. It has internal structure. It has remnants. It has bones. Some researchers have interpreted this filament as evidence that the Boötes void may have formed from the merger of smaller voids. In the standard picture of cosmic structure formation, voids grow over time as matter drains out of underdense regions and accumulates in the surrounding walls and filaments. When two adjacent voids expand far enough, the thin wall of galaxies separating them gets stretched and thinned. Eventually, the wall dissolves, and the two voids merge into one larger void. The leftover galaxies from the former wall do not vanish. They linger. They drift. They form a faint strand, a ghost of the boundary that once separated two emptinesses. If this interpretation is correct, the tube of galaxies inside the Boötes void is a fossil. It is the remains of a wall that once divided smaller voids billions of years ago. Over cosmic time, those voids expanded. The wall disintegrated, and the resulting merged structure became the behemoth we observe today. This idea carries enormous implications for how the void reached its current size, and for what it tells us about the limits of gravitational evolution in a universe only 13.8 billion years old. Now, let us place the Boötes void in context against other known cosmic voids, because it does not exist in isolation. The universe is riddled with voids. They are one of the most common features of the large-scale structure. The cosmic web is as much defined by its holes as by its filaments. Without the voids, the web would not have its characteristic sponge-like topology. Surveys like the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey have catalogued hundreds of voids across the observable universe. Most of them fall within a size range of roughly 30 to 300 million light-years in diameter. The smaller ones are common. They are unremarkable. They fit neatly within the predictions of our cosmological models. The larger ones are rarer. They sit at the upper end of the distribution. They require longer stretches of uninterrupted gravitational evolution to form, or they require the merger of smaller voids. Within this distribution, the Boötes void occupies a position at or near the extreme upper end. There are a few other supervoids that approach its scale. The KBC void, identified more recently, may be even larger, though its definition and boundaries are debated. the CMB cold spot, a region of anomalously low temperature in the cosmic microwave. Background has been associated with a large foreground void, though the relationship is complex and not fully settled. These structures form a small family of extreme outliers that sit uncomfortably at the edge of what the standard model can comfortably produce. But even among this family, the Boötes void holds a special place. It was the first to be discovered. It is one of the best studied, and its combination of size and emptiness makes it one of the most striking features in the observable universe. To appreciate just how striking, consider one final comparison. The observable universe has a diameter of roughly 93 billion light-years. This is not the size of the entire universe, which may be far larger or even infinite. It is simply the size of the sphere from which light has had time to reach us since the Big Bang. Within this sphere, everything we can see, every galaxy, every star, every photon, is contained. The Boötes void, at 330 millionths light-years across, represents roughly 0.35% of the diameter of the observable universe. That sounds small. It sounds like a rounding error. But remember, we are talking about a three-dimensional volume. Volume scales as the cube of the diameter. The volume of the Boötes void, while a tiny fraction of the total observable universe, is still staggering in absolute terms. It is one of the single largest coherent structures ever identified, and it is defined not by the presence of matter, but by its absence. Think about what it takes to earn the title of one of the largest structures in the universe by being empty. The Great Wall, the Sloan Great Wall, the Hercules Corona Borealis Great Wall. These are among the largest known structures, and they are defined by concentrations of galaxies. They are notable because of what they contain. The Boötes void is notable because of what it does not contain. It is a monument to nothing, a landmark made of absence. And that absence is what keeps astronomers up at night. Not because they are afraid of the dark, but because the dark is too big. The emptiness is too complete. The structure is too extreme. The models we trust, the simulations we run, the physics we rely on, they all struggle to produce something this large and this barren within the age of the universe. The scale of the Boötes void is not just a number. It is a challenge to our understanding of how gravity assembles the cosmos. A challenge to the initial conditions that seeded all structure. A challenge to the statistical machinery we use to test our theories against observation. And the deeper we push into that challenge, the more we realize that this emptiness is not passive. It is not just sitting there. It is telling us something about the forces that built the universe. It is telling us something about the rules of the game. And to decode that message, we need to understand the language. We need to understand how the universe builds its structures in the first place. We need to look at the cosmic web, the machinery of gravity, and the delicate physics of void formation. Because only when we understand how voids are supposed to form, can we understand why this one is so deeply, disturbingly wrong. To understand why the Boötes void is a problem, you first need to understand what the universe is supposed to look like. You need to see the blueprint, because the Boötes void is not just a random patch of emptiness floating in space. It is a deviation from a pattern. And you cannot appreciate a deviation until you understand the pattern it deviates from. So let us build the universe from scratch. Let us go back to the very beginning and watch the architecture assemble itself. Because the story of the cosmic web, the vast network of galaxies and voids that fills the observable universe, begins not with galaxies. It begins with sound. Roughly 13.8 billion years ago, the universe was born. We call this event the Big Bang, although the name is misleading. It was not an explosion in space. It was an expansion of space. There was no center. There was no edge. There was no pre-existing emptiness that suddenly filled with matter. Space itself came into existence and immediately began to stretch. And within that stretching space, matter and energy were packed together at temperatures and densities so extreme that the physics governing them was fundamentally different from anything we experience today. In those first moments, the universe was a plasma, a blinding fog of subatomic particles and radiation so hot and so dense that light could not travel freely. Photons bounced between particles like pinballs, scattering endlessly, unable to fly in a straight line for more than a tiny fraction of a second. The universe was opaque. If you had eyes and could somehow survive the conditions, you would see nothing. Just a white-hot wall of light in every direction with no structure, no depth, no form. But the universe was not perfectly smooth. And this imperfection is the single most important fact in all of cosmology. Because without it, you would not exist. The Milky Way would not exist. No galaxy, no star, no planet, no atom of carbon in your body would exist. The universe would be a featureless, uniform soup of particles, expanding forever into an ever-colder oblivion. The imperfections were tiny, almost inconceivably tiny. They were fluctuations in the density of matter, variations so small that they amounted to roughly 1 part in 100,000. Imagine a perfectly still lake. Now imagine a ripple so faint that the surface rises by 100,000th of a millimeter. That is the scale of the density variations in the early universe. In some regions, the density of matter was a tiny fraction higher than average. In others, it was a tiny fraction lower. These fluctuations were random. They had no preferred direction, no preferred scale. They were scattered across all sizes like static on a radio tuned to no station. Where did these fluctuations come from? The leading theory is that they originated from quantum mechanics. In the very first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called inflation. During inflation, space expanded by a factor of at least 10 to the power of 26 in a time span shorter than a trillionth of a trillionth of a trillionth of a second. This expansion was so violent that it took the tiny quantum fluctuations that naturally exist at subatomic scales and stretched them to cosmic proportions. Random jitters in the quantum vacuum became the seeds of all future structure. They became the blueprint for the cosmic web. We can actually see these seeds. They are imprinted on the oldest light in the universe, the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. When this happened, the fog lifted. Photons were suddenly free to travel in straight lines. They streamed outward in every direction and have been traveling ever since. Today, those photons fill the entire sky as a faint bath of microwave radiation, with an average temperature of about 2.7 degrees above absolute zero. This is the cosmic microwave background, the CMB. It is the afterglow of the Big Bang, a snapshot of the universe as it looked when it was less than 400,000 years old. When we map the CMB with exquisite precision, as satellites like COBE, WMAP, and Planck have done, we see something remarkable. The temperature is almost perfectly uniform across the entire sky. But not quite. There are tiny variations. Spots that are slightly warmer, and spots that are slightly cooler, by a few millionths of a degree. These hot and cold spots correspond directly to the density fluctuations in the early universe. The warm spots are regions where matter was slightly more concentrated. The cool spots are regions where matter was slightly less concentrated. This map of temperature variations is, in a very real sense, the baby photo of the cosmic web. It shows us where the filaments will form and where the voids will open up. Every galaxy cluster that exists today, every vast wall of galaxies, every enormous void, they all have their origins in these faint smudges on the cosmic microwave background. The blueprint was drawn 380,000 years after the Big Bang. The universe spent the next 13 billion years building the structure. So how did these faint ripples become the cosmic web? The answer is gravity. Patient, relentless, and spectacularly creative gravity. Consider a region of the early universe where the density is slightly higher than average. Just a tiny bit more matter than the surrounding regions. That extra matter exerts a slightly stronger gravitational pull. It tugs on the surrounding material, drawing it inward. As more matter falls in, the density increases further, which strengthens the gravitational pull, which draws in even more matter. This is a positive feedback loop, a snowball effect. Gravity amplifies the initial fluctuation. The rich get richer. Now consider the opposite. A region where the density is slightly lower than average. There is less matter here, which means weaker gravitational pull. The surrounding denser regions are more attractive. Matter migrates away from the underdense region toward the overdense regions. The underdense region loses matter, becoming even more underdense. The poor get poorer. The void deepens. This process, the gravitational amplification of initial density fluctuations, is the engine that builds the cosmic web. It operates simultaneously across all scales. Small fluctuations produce small structures, large fluctuations produce large structures. And because the initial fluctuations exist at every scale, the resulting structure has features at every scale too. From individual galaxies to clusters of galaxies to superclusters to the vast filaments and walls that stretch across hundreds of millions of light years. But gravity does not work alone. It has collaborators. And the most important collaborator, the silent partner in the construction of the cosmic web, is dark matter. Dark matter is one of the most mysterious substances in the universe. We cannot see it. We cannot touch it. It does not emit light. It does not absorb light. It does not interact with ordinary matter through any force except gravity. And yet, it outweighs ordinary matter by a factor of roughly 5 to 1. For every kilogram of atoms in the universe, the stuff that makes up stars and planets and you, there are approximately 5 kilograms of dark matter. It is the dominant form of matter in the cosmos, and it is the scaffolding on which the entire cosmic web is built. Here is why dark matter matters for structure formation. In the early universe, ordinary matter was coupled to radiation. The photons and the particles were locked together in the plasma, bouncing off each other, unable to separate. This coupling created pressure, and pressure resists gravitational collapse. When gravity tried to pull ordinary matter into the denser regions, radiation pressure pushed back. The matter oscillated. It sloshed back and forth like water in a bathtub. These oscillations are called baryon acoustic oscillations, and they left a characteristic pattern in the cosmic microwave background and in the distribution of galaxies that we can measure today. But dark matter does not interact with photons. It has no radiation pressure. It is immune to the sloshing. So while ordinary matter was bouncing around, dark matter was quietly collapsing. It was falling into the gravitational potential wells created by the initial density fluctuations and building up structure. By the time the universe cooled enough for ordinary matter to decouple from radiation, dark matter had already formed a network of dense clumps and filaments, a skeleton, a framework, and when ordinary matter was finally free to fall, it fell into the dark matter scaffolding. It followed the path that dark matter had already laid out. This is why dark matter is so critical. Without it, the density fluctuations in ordinary matter alone would not have had time to grow into the structures we see today. The universe is only 13.8 billion years old. Gravity working on ordinary matter alone, fighting against radiation pressure for the first few 100,000 years, would not have produced galaxies and clusters and filaments by now. The math does not work. The growth rate is too slow. Dark matter gives gravity a head start. It begins collapsing earlier and creates the gravitational scaffolding that ordinary matter later fills in. The result of this process, played out over billions of years across the entire observable universe, is the cosmic web. Picture it. Imagine you could zoom out far enough to see hundreds of millions of light years at a glance. What you would see is a structure that looks eerily organic. It looks like a neural network, or a cross-section of bone marrow, or the branching pattern of blood vessels. There are dense nodes where thousands of galaxies are packed together in massive clusters. Connecting these nodes are long, thin filaments, bridges of galaxies and dark matter that stretch across tens or hundreds of millions of light years. Between the filaments are broad, flat walls, sheets of galaxies that form the boundaries between enormous empty regions. And occupying the spaces between the walls, filaments, and nodes are the voids. Vast, roughly spherical regions where the density of matter drops to a fraction of the cosmic average. This pattern is not random. It is not chaotic. It is the natural, inevitable outcome of gravity amplifying random density fluctuations in a universe dominated by dark matter and driven apart by the expansion of space. The physics is deterministic, given the initial conditions. If you know the pattern of density fluctuations at the time of the cosmic microwave background, and if you know the composition of the universe, how much dark matter, how much ordinary matter, how much dark energy, then you can predict, statistically, what the cosmic web should look like today. And this is exactly what cosmologists do with n-body simulations. An n-body simulation is one of the most powerful tools in modern astrophysics. The concept is straightforward in principle, but staggering in practice. You take a large volume of virtual space, you fill it with billions of particles, each representing a clump of dark matter. You assign each particle a position and a velocity based on the density fluctuations observed in the cosmic microwave background. And then you let gravity do its work. The simulation calculates the gravitational force between every pair of particles. It updates their positions. It advances the clock by a small time step. Then it calculates the forces again, and again, and again. Billions of particles, each pulling on every other particle, step by step, from the conditions of the early universe to the present day. The computation is immense. The largest modern simulations, projects like the Millennium simulation, Illustri's TNG, and the Bolshoi simulation, track hundreds of billions of particles in volumes spanning billions of light years. They require supercomputers running for months. But the results are extraordinary. When these simulations finish, when the virtual universe has evolved from its smooth initial state to the present epoch, the output looks almost indistinguishable from the real universe. The simulations produce filaments, walls, clusters, and voids. They produce a cosmic web whose statistical properties, the distribution of galaxy clusters, the correlation functions, the void size distribution, match the observed universe with remarkable fidelity. The standard cosmological model, known as lambda c dm, which combines a cosmological constant representing dark energy with cold dark matter, reproduces the large-scale structure of the universe with stunning success. This success extends to voids. The simulations predict that voids should form naturally as matter evacuates underdense regions and piles up in the surrounding filaments and walls. They predict a range of void sizes, from modest pockets a few tens of millions of light years across to larger emptinesses exceeding 100 million light years. They predict that voids should be roughly spherical, that their interiors should be underdense but not completely empty, and that their edges should transition gradually into the denser cosmic web. All of these predictions match the observations. But here is where we need to pay close attention. Because the agreement between simulations and observations is statistical. It is an agreement about averages. It says that the overall distribution of void sizes, the typical density profile of a void, the general topology of the cosmic web, all of these match. It does not say that every individual structure in the real universe has an exact counterpart in the simulation. It cannot. The simulations start from random initial conditions drawn from the same statistical distribution as the real universe, but they are not starting from the actual initial conditions of our specific universe. They are running different random seeds, they are building different cosmic webs that share the same statistical properties. This distinction matters, because when we ask whether the Boötes void is consistent with lambda CDM, we are not asking whether a specific simulation produced a void in the exact location and with the exact size of the Boötes void. We are asking whether the statistical distribution of voids predicted by the model includes objects as large and as empty as the Boötes void with reasonable probability. And the answer to that question is where the discomfort begins. The simulations predict a characteristic distribution of void sizes. The vast majority of voids are modest. Most fall below 100 million light-years in diameter. Larger voids exist but become progressively rarer. A void of 200 million light-years is uncommon. A void of 300 million light-years is very uncommon. The probability drops steeply with increasing size. The reason for this steep drop is rooted in the physics of gravitational evolution. Voids grow because matter evacuates them, but this evacuation takes time. The rate at which a void expands depends on the density contrast, how much emptier the void is compared to its surroundings, and on the expansion rate of the universe. In a universe that is only 13.8 billion years old, there is a limit to how large a single void can grow from a single initial underdensity. The clock runs out before the void can reach truly enormous proportions. This is why the idea of void mergers is so important. If a single void cannot grow to 330 million light-years on its own within the age of the universe, then perhaps the Boötes void is not a single void at all. Perhaps it is the result of several smaller voids that formed independently, expanded, and eventually merged into one colossal empty region. The ghostly filament of galaxies threading through the void's interior, which we encountered earlier, may be the fossil evidence of exactly this process. The remnant of a wall that once separated two smaller voids before they swallowed each other. But mergers have limits. The walls between voids do not dissolve instantaneously. The gravitational dynamics of wall dissolution involve the slow migration of galaxies away from the thinning wall and into the denser structures at the void edges. A single merger event can take billions of years. A cascade of mergers takes even longer. So the question is whether the age of the universe provides enough time for a sufficient number of mergers to produce something as large as the Boötes void. The answer from simulations is that it is possible, but it requires a specific set of favorable initial conditions. You need a region of the early universe where several adjacent underdensities were clustered together, each one slightly below average density, arranged in a configuration that would allow their eventual merger. This arrangement is not impossible. It is a natural fluctuation of the initial density field, but it is not common. This brings us to the crux of the issue. The Boötes void is consistent with the lambda CDM model in the sense that the model does not absolutely forbid it. The physics allows it. The simulations can produce it under the right initial conditions. But those conditions are rare. The probability of finding a void this large and this empty within a given survey volume is low. How low depends on the details of the analysis, the exact void definition used, and the volume of the simulation. Different studies have reached slightly different conclusions, but the general consensus is that the Boötes void sits near the edge of the expected distribution. It is not a comfortable prediction. It is a grudging concession. The model allows it, but it does so while raising an eyebrow. And this is where the scientific unease lives. Not in outright contradiction, not in a dramatic failure of the model, but in a persistent nagging sense that this structure is pushing the envelope. That it is asking the model to do something that the model can technically do, but does not particularly want to do. Think of it this way. If you flip a fair coin 100 times and get 97 heads, the coin is not necessarily rigged. The probability of getting 97 or more heads is tiny, about 1 in a billion, but it is not zero. The laws of probability technically allow it. But if it happened to you, you would not shrug and say, well, it was possible. You would pick up the coin and examine it very carefully. You would suspect that something about your understanding of the coin was incomplete. The Boötes void is the 97 heads. It is not proof that the model is wrong, but it is the kind of result that makes careful scientists put down their pens and stare at the wall for a while. It is the kind of result that motivates people to look harder at the initial conditions, to refine the simulations, to double-check the observations, and to ask whether there might be additional physics at play that the standard model does not yet capture. There is one more ingredient in this cosmic recipe that we need to discuss. We have talked about gravity pulling matter together and creating dense regions. We have talked about matter evacuating voids and leaving them empty. But we have not yet talked about the force that accelerates this evacuation, the force that pushes the voids to expand faster than gravity alone would predict. That force is dark energy. Dark energy is the dominant component of the universe. It constitutes roughly 68% of the total energy density of the cosmos. It does not clump. It does not form structures. It fills space uniformly, and it has a single defining property. It drives the accelerating expansion of the universe. In the dense regions of the cosmic web, the filaments and clusters, gravity is strong enough to overcome the expansion. Matter is bound together. Galaxies orbit within clusters. The local gravitational pull holds the structure intact. But in the voids, matter is sparse, gravity is weak, and dark energy wins. The expansion of space inside a void is not slowed down by gravitational attraction. It is accelerated by dark energy. This means that voids do not just grow because matter leaves them. They grow because the space inside them is stretching, faster than the space inside the dense regions. Dark energy acts as a void inflator. It amplifies the emptiness. It takes a modest underdensity and turns it into a gaping chasm. And the emptier the void becomes, the less gravity there is to resist the expansion, which means the expansion accelerates further, which makes the void even emptier. Another positive feedback loop. Gravity builds the walls, dark energy blows up the bubbles. This interplay between gravity and dark energy is what sculpts the cosmic web into the structure we observe today. The filaments and clusters are the bones. The voids are the lungs. And the whole system breathes, driven by the tension between the attractive force that builds and the repulsive force that expands. The Buddha's void is one of the deepest breaths the universe has ever taken. And the question that haunts cosmologists is whether that breath was just a natural variation in the rhythm, or whether it signals something unexpected about the lungs themselves. Now we have the tools to confront the anomaly directly. We understand how voids form. We understand the role of gravity, dark matter, and dark energy. We understand what the simulations predict, and where the predictions become uncomfortable. So let us press our thumbs directly into the bruise. Let us examine in precise detail why the Boötes void refuses to sit quietly inside our models, and what that refusal might mean. We have built the machinery. We understand how the universe assembles its grand architecture. Gravity pulls, dark matter scaffolds, dark energy inflates, fluctuations grow, walls thicken, voids deepen. The cosmic web emerges from the interplay of these forces like crystal structure forming in a cooling liquid. It is elegant, it is predictable, and for the vast majority of the observable universe, it works. But now we have to deal with the thing that does not quite work. We have to look directly at the Boötes void and ask the question that has been simmering beneath this entire story. Why is it so big? Why is it so empty? And why does it make cosmologists uncomfortable? Let us start by being precise about the discomfort, because this is not a case where the observations flatly contradict the theory. It is subtler than that. It is the kind of tension that lives in the margins of a probability distribution. The kind that does not scream at you. It whispers. And the whisper says something might be off. The lambda CDM model, the standard model of cosmology, makes statistical predictions about the distribution of cosmic structures. It does not tell you exactly where each galaxy cluster will form, or where each void will open up. It tells you the likelihood of finding structures of various sizes in a given volume of space. It gives you a probability distribution, a bell curve with a peak and tails. For voids, this distribution has a characteristic shape. Small voids are common, medium voids are less common, large voids are rare, and extremely large voids, those exceeding 250 or 300 million light years, are very rare. The curve drops off steeply at the high end. This steep decline is not arbitrary. It is a direct consequence of the physics we have been building toward. Voids grow through the evacuation of matter and the merging of smaller voids. Both processes take time, and the universe is only 13.8 billion years old. There has been a limited window of opportunity for voids to grow, which places a natural ceiling on how large they can become. The Boötes void, at approximately 330 million light-years in diameter, sits at or beyond the tail of this distribution. The exact probability of finding such a void depends on the details of the analysis. How do you define the boundary of a void? What density threshold do you use? What survey volume are you comparing against? Different research groups have made different choices, and the results vary. But the general picture is consistent. The Boötes void is an outlier. Some analyses place it within the 95th percentile of the expected void size distribution. Others push it further out to the 99th percentile or beyond. In plain language, this means that if you ran the simulation of the universe 100 times with different random initial conditions, you might find a void this large in only one or a handful of those runs. It is not impossible, but it is the kind of event that raises questions. To understand why this matters, think about what it means to be at the tail of a distribution. If you measure the heights of 10,000 adult men and find one who is 7 feet 6 inches tall, you do not panic. That is unusual, but within the expected range of human variation. But if you find one who is 9 feet tall, you start asking questions. Is the measurement correct? Is there a medical condition at work? Is your model of human height missing something? The Boötes void is not the 9-foot man. It is more like the 8-foot man, tall enough to make you look twice, tall enough to make you wonder whether your understanding of the growth process is complete. Now, let us examine the specific features of the Boötes void that contribute to this tension. The first is its sheer volume. A sphere 330 million light-years across has a diameter of roughly 100 megaparsecs in the units cosmologists prefer. A megaparsec is about 3.26 million light-years. That gives the void a volume of approximately 500,000 cubic megaparsecs. That is an enormous volume. It represents a significant fraction of the survey volumes used in modern redshift surveys. Finding a single coherent underdense region occupying this much space is remarkable, because it implies a correspondingly large-scale coherence in the initial density field. What does that mean? It means that the primordial fluctuation that seeded the Boötes void was not a small, localized dip in density. It was a broad, extended depression stretching across a region that would eventually grow to hundreds of millions of light years. The fluctuation had to be correlated across that entire scale. The initial conditions had to conspire, in a loose sense, to create a coherent underdensity of this magnitude and this extent. In the standard model, the initial density fluctuations are drawn from a Gaussian random field. This means their amplitudes follow a bell curve distribution, and their correlations fall off predictably with distance according to a power spectrum. The power spectrum we measure from the cosmic microwave background tells us how much fluctuation exists at each spatial scale. It is remarkably well determined. We know it with high precision, and it tells us that fluctuations on very large scales, the scales relevant to the Boötes void, have relatively small amplitudes. The power spectrum decreases at the largest scales. There is less room for extreme fluctuations. This is part of why the Boötes void is challenging. The initial fluctuation that seeded it had to be a relatively rare excursion from the mean density. Not catastrophically rare, not impossible, but uncommon. And when you combine this with the finite time available for gravitational evolution and void merging, the probability of producing the final observed structure becomes small. The second troublesome feature is the degree of emptiness. It is one thing to have a large void. It is another to have a large void that is also exceptionally underdense. The Boötes void is not just big, it is remarkably barren. The void's interior density, as we have seen, is roughly 2 to 5% of the cosmic mean, depending on how the calculation is performed. This level of emptiness requires sustained and efficient evacuation of matter over cosmic time. It requires that the gravitational dynamics and the dark energy-driven expansion have been working in concert, relentlessly, clearing matter from the interior and piling it up on the edges. In simulations, voids this empty do occur, but they tend to be smaller. The largest voids in simulations are often not the emptiest, and the emptiest voids are often not the largest. The Boötes void combines both properties simultaneously. It is both very large and very empty. This combination is what makes it particularly rare in the simulated void population. Think of it as a two-dimensional problem. You have a scatter plot where the horizontal axis is void diameter and the vertical axis is internal density. Most voids cluster in the middle of the plot. A few scatter toward large diameter. A few scatter toward low density. But the corner of the plot where diameter is very large and density is very low is sparsely populated. The Boötes void sits in that corner. It occupies a region of parameter space that simulations can access, but only infrequently. The third feature worth examining is the internal structure. Remember the tube-like filament of galaxies threading through the interior of the void. This structure has been studied by several groups, and its existence suggests that the Boötes void is not a simple, pristine bubble that grew from a single underdensity. It appears to be a composite structure, a merged entity. If the void formed from the coalescence of two or more smaller voids, then the internal filament may be the remnant of the wall that once separated them. This is a natural prediction of the merger model. When two voids merge, the wall between them thins and fragments, but it does not disappear instantaneously. Galaxies that were part of the wall get stranded in the interior of the newly merged void. They drift apart slowly, forming a loose chain or filament that gradually disperses over billions of years. The fact that this filament is still visible today suggests that the merger happened relatively recently, in cosmic terms. If the merger had occurred very early in the history of the universe, the filament would have had time to fully disperse. Its galaxies would be scattered randomly throughout the void, indistinguishable from a uniform low-density background. But the filament is still coherent. It is still recognizable as a linear structure. This implies that the merger process is either ongoing or was completed within the last few billion years. This has implications for the formation timeline. If the Boötes void is a merger product, then its current size reflects not just the growth of a single void over 13.8 billion years, but the combined growth and eventual coalescence of multiple voids. The question is whether the merger scenario makes the void easier or harder to explain. On one hand, mergers provide a mechanism for reaching the observed size. A single void growing from a single seed might struggle to reach 330 million light-years within the available time, but 2 or 3 voids, each growing to 150 or 200 million light-years independently, could merge to produce the observed structure. This is more plausible in terms of growth rate. On the other hand, the merger scenario requires a specific spatial arrangement of initial underdensities. You need multiple adjacent underdensities in the primordial density field, close enough to each other that their respective voids will eventually overlap. This is a constraint on the initial conditions. It is not a severe constraint. Such configurations do arise naturally in a Gaussian random field, but it adds another layer of improbability. You need not just one rare fluctuation, but a cluster of fluctuations arranged in the right configuration. When cosmologists attempt to quantify the overall probability of the Boötes void under lambda CDM, they must account for all of these factors: the size, the emptiness, the internal structure, the required initial conditions, the available time for evolution, the result is a probability that is small but not vanishingly small. The void is improbable, not impossible. It is the kind of structure that might appear once in a survey volume the size of the observable universe, or it might not appear at all. This brings us to a subtle but important point about how scientists evaluate the significance of anomalies. In any sufficiently large dataset, you will find outliers. This is guaranteed by statistics. If you measure the sizes of every void in the observable universe, the largest one will, by definition, be at the extreme end of the distribution. It has to be. Something has to be the biggest. The question is whether the biggest one is bigger than the distribution predicts the biggest one should be. This is called the look elsewhere effect. If you search hard enough, in enough places, you will always find something unusual. The key is whether the anomaly remains significant after you account for the number of places you looked. A single unlikely event in a single observation is striking. A single unlikely event in a billion observations is expected. For the Boötes void, the look elsewhere effect cuts both ways. On one hand, the observable universe is enormous. It contains hundreds of thousands of voids. The fact that the single largest one is very large is not, by itself, alarming. Something has to be the record holder. On the other hand, the Boötes void is not just marginally larger than the next biggest void. It is substantially larger. It sits noticeably above the expected maximum for a lambda CDM universe of our survey volume. The gap between the observed extreme and the predicted extreme is what concerns people. Several research groups have attempted to quantify this gap using different statistical tools. Some have used extreme value statistics, a branch of probability theory specifically designed to analyze the behavior of the largest or smallest values in a dataset. Others have used direct comparison with simulation catalogs, counting how many voids in their simulated universes match or exceed the Boötes void in size and emptiness. The results are not uniform, but they generally point in the same direction. The Boötes void is unlikely under lambda CDM. Not fatally unlikely, not crisis level unlikely, but unlikely enough to deserve attention. And the Boötes void is not the only large-scale anomaly in the universe. It is part of a pattern. In 2004, astronomers examining data from the Wilkinson Microwave Anisotropy Probe, WMAP, identified a puzzling feature in the cosmic microwave background. There was a region of the sky, roughly 10 degrees across in the direction of the constellation Eridanus. That was significantly colder than the surrounding CMB. This cold spot, as it became known, was too large and too cold to be easily explained by the standard Gaussian fluctuations of the CMB. Its statistical significance was debated, but it attracted widespread attention. One proposed explanation for the cold spot was a large foreground void. The idea, developed through a mechanism called the integrated Sachs-Wolf effect, works as follows. When a photon from the cosmic microwave background passes through a void, it encounters a gravitational potential hill. A void has less mass than its surroundings, so entering one is like climbing uphill. The photon expends energy as it enters, losing a tiny amount to gravitational redshift. As it exits the other side and returns to denser space, it descends the hill and regains energy through gravitational blue shift. In a universe without dark energy, these two effects cancel perfectly. The photon exits with the same energy it entered with. But in a universe with dark energy, the void is expanding and becoming shallower while the photon is traveling through it. The potential hill that the photon descends on the way out is flatter than the one it climbed on the way in. So it regains slightly less energy leaving than it spent entering. The photon exits with a net loss of energy. It becomes slightly redshifted. In the CMB map, this appears as a cold spot. For this mechanism to produce a cold spot as large and as pronounced as the one observed, the foreground void would have to be enormous. Some estimates suggested a void on the order of several 100 million light-years across, located at a distance of a few billion light-years. Surveys aimed at testing this hypothesis found evidence for a large underdensity in the right region of sky, though whether it is sufficient to fully explain the cold spot remains debated. Some studies argue the void is too shallow. Others argue the alignment is compelling. The point is not to settle the cold spot debate here. The point is that the Boötes void is not alone in posing challenges to our expectations about large-scale structure. There appear to be several features in the universe, including other supervoids identified in more recent surveys, that cluster near the boundaries of what lambda CDM predicts. Individually, each one can be waved away as a statistical fluctuation. Collectively, they begin to form a pattern that warrants scrutiny. This is the nature of the tension. It is not a single smoking gun. It is a collection of circumstantial evidence. A jury of scientists looking at any one piece might say that is odd but not conclusive. But as the pieces accumulate, the collective weight starts to shift the balance, not toward rejection of the model. Lambda CDM is far too successful for that, but toward the suspicion that the model might be incomplete, that there might be additional physics at work on the larger scales that we have not yet identified. What kind of additional physics? This is where speculation begins, and we need to tread carefully. But several ideas have been floated. One possibility involves the nature of dark energy. In the standard model, dark energy is treated as a cosmological constant. Its density is uniform across space and constant, in time. But what if dark energy is not constant? What if it varies either in space or in time or both? Some models of dark energy, known as quintessence models, allow for a dynamical dark energy field that can fluctuate. If dark energy were slightly stronger in some regions and slightly weaker in others, it could differentially accelerate the expansion of voids, making some voids larger and emptier than the standard model predicts. The Boötes void could be a region where a local enhancement of dark energy supercharged the void's expansion, pushing it beyond the expected size. This is speculative. There is no direct evidence for spatial variation in dark energy, but the possibility has not been ruled out, and the existence of anomalously large voids provides motivation to investigate it. Another possibility involves the initial conditions. We said earlier that the initial density fluctuations are assumed to be Gaussian, meaning their amplitudes follow a bell curve distribution. This is a simplifying assumption that is supported by the data from the cosmic microwave background to high precision, but it is not guaranteed to be exact. Small deviations from Gaussianity, known as non-Gaussianity, are predicted by some models of inflation and could affect the probability of extreme structures. If the initial fluctuations had a slightly non-Gaussian distribution, the tails of the distribution could be fatter or thinner than expected. Fatter tails would mean more extreme fluctuations, both over densities and under densities, which could produce more extreme structures, including very large voids. This is another avenue that the Boötes void motivates researchers to explore. A third possibility is more prosaic, but equally important. Perhaps our measurements of the void are not yet precise enough. The boundary of a void is not a sharp wall. It is a gradual transition. Different algorithms for identifying and measuring voids can produce different size estimates for the same structure. If the true diameter of the Boötes void is closer to 250 million light-years than 330 million light-years, the tension with lambda CDM decreases significantly. The void moves from the extreme tail of the distribution to the merely unusual portion. This is not a glamorous explanation. It does not invoke new physics, but it is a real possibility that must be taken seriously. The honest answer, the answer that reflects the current state of knowledge, is that we do not yet know whether the Boötes void represents a genuine crack in the standard model or simply a rare but permitted fluctuation. The data is not conclusive in either direction. The void is too big to ignore, but not big enough to break the theory. It sits in the most frustrating possible location on the probability spectrum. Uncomfortably unlikely, but not impossibly so. This is why it generates unease rather than crisis. A crisis would be easier to deal with. A crisis would mean a clear signal that the model is wrong, which would motivate a focused search for a replacement. But the Boötes void does not give us that clarity. It gives us ambiguity. It gives us a nagging feeling that something might be slightly off without telling us what. And that, in many ways, is more unsettling than a clean break. A clean break is a signpost. It tells you where to go. An anomaly that hovers at the edge of significance is a fog. You can see shapes in it, but you cannot tell whether they are real or imagined. You squint, you strain, you run more simulations, you collect more data, and the fog does not lift. It just sits there, patient and indifferent, waiting for you to build a better telescope or a better theory. The Boötes void is that fog. It has been sitting in the northern sky for over 4 decades, ever since Kirshner and his colleagues first noticed the hole in their data. Surveys have gotten deeper. Simulations have gotten larger. Statistical methods have gotten more sophisticated. And the void has not budged. It has not shrunk. It has not turned out to be a measurement error. It has not been explained away by a clever reanalysis. It is still there. Still too big. Still too empty. Still asking the same quiet question. Is your model complete? The answer for now is we think so. Probably. Mostly. But we are not certain. And in science, the absence of certainty is not a failure. It is an invitation. An invitation to look harder, think deeper, and remain honest about what we do not know. The Boötes void is one of the most honest objects in the universe. It does not pretend to be anything. It does not dazzle with light or radiation. It does not announce itself with dramatic signals. It simply presents its emptiness and lets the numbers speak. And the numbers say something very simple. I am here. I am real. And I am bigger than you expected. What are you going to do about it? That question does not just apply to the statistics. It reaches deeper. It touches the most fundamental assumptions we carry about how reality is organized. And that is where the emptiness becomes truly unsettling. We have spent this entire journey looking at the Boötes void from the outside. We measured it. We mapped it. We ran it through simulations. We compared it to probability distributions and stress tested it against the standard model. We have treated it as a problem to be solved, an anomaly to be explained, a number that does not quite fit inside the box we built for it. But now we need to do something different. We need to stop measuring and start listening. Because the Boötes void is not just a problem in cosmology, it is a message written in the language of absence. And if we read it carefully, it tells us something profound about the universe we inhabit. Something that goes beyond the technical question of whether lambda CDM can produce a void this large. Something that touches the deepest assumptions we carry about how reality is organized. Let us begin with the most fundamental of those assumptions. The cosmological principle. We introduced this idea earlier. The universe on sufficiently large scales is supposed to look the same everywhere and in every direction. We noted that the Boötes void raised uncomfortable questions about this assumption, but now we can be more precise about why, because the discomfort is not abstract. It is quantitative, and the numbers land in an awkward place. The cosmological principle is supposed to hold on sufficiently large scales, but what counts as sufficiently large? This is not a settled question. Different analyses give different answers. Some studies suggest that the universe becomes statistically homogeneous at scales of roughly 250 to 300 million light-years. Others argue the transition does not occur until scales of 500 million light-years or more. The Boötes void, at 330 million light-years across, straddles this boundary. It is large enough to be comparable to the scale at which homogeneity is supposed to emerge. And yet, it is a dramatic departure from the average density. It is a feature whose very existence demonstrates that on scales of hundreds of millions of light-years, the universe is decidedly not uniform. This does not kill the cosmological principle, but it does make us reckon with its limitations. It reminds us that the principle is an approximation, not a law. The universe does not owe us smoothness. It gave us a web. A wild, tangled, lumpy web with dense knots and gaping holes. And the Boötes void is the largest hole we have found. It sits right at the boundary of where our assumption of uniformity is supposed to kick in, daring us to defend that assumption with something more rigorous than habit. Let us go deeper. Let us think about what the void tells us about the initial conditions of the universe. Every structure in the cosmic web, every filament, every cluster, every void, traces its ancestry back to the primordial density fluctuations imprinted during inflation. The pattern of hot and cold spots in the cosmic microwave background is the genetic code of the universe. It encodes the instructions for every structure that will ever form. The Boötes void exists because somewhere in that ancient pattern, there was a broad, coherent underdensity, a region where the density of matter was slightly below average across a vast stretch of the primordial field. We touched earlier on the possibility that these primordial fluctuations might not be perfectly Gaussian, that the tails of the distribution might be subtly fatter than the standard assumption predicts. But here is where that possibility becomes operationally powerful. The Boötes void is not just sensitive to non-Gaussianity, it is one of our best tools for measuring it. Voids are in some ways better probes of the initial conditions than clusters. Galaxy clusters form in the densest peaks of the initial field, and their properties are heavily modified by the complex physics of gas cooling, star formation, and feedback. Voids, by contrast, are relatively pristine. Their interiors have been largely emptied of the messy astrophysical processes that complicate the study of dense regions. What remains is closer to the pure gravitational signal. The void is a cleaner fossil of the initial conditions than a cluster could ever be. This is not idle speculation. Several research programs are actively using the statistics of cosmic voids, including extreme voids, to constrain primordial non-Gaussianity. Voids are, in some ways, better probes of the initial conditions than clusters. Galaxy clusters form in the densest peaks of the initial field, and their properties are heavily modified by the complex physics of gas cooling, star formation, and feedback. Voids, by contrast, are relatively pristine. Their interiors have been largely emptied of the messy astrophysical processes that complicate the study of dense regions. What remains is closer to the pure gravitational signal. The void is a cleaner fossil of the initial conditions than a cluster could ever be. The Boötes void, as the most extreme void known, sits at the sharpest edge of this probe. It is the data point with the most leverage. If future measurements refine its size and density profile, and if improved simulations narrow the predicted void size distribution, the Boötes void could become a powerful test of inflation. It could tell us something about the quantum processes that occurred in the first fraction of a second after the Big Bang. The emptiness of a region 330 million light-years across, mapped by 20th and 21st century telescopes, could carry information about physics at energies trillions of times higher than anything we can produce in a laboratory. That is the extraordinary reach of observational cosmology. The largest structures in the universe are windows into the smallest moments of its birth. Now, let us consider what the void tells us about dark energy. We have already seen how dark energy accelerates the expansion inside voids, creating a feedback loop that deepens the emptiness. But the Boötes void lets us push this further. Its interior is one of the places in the universe where dark energy has the least competition from gravity. If dark energy behaves differently than we expect, if it varies in strength across space, if it evolves over time, if it interacts with matter in subtle ways, those effects would be amplified inside the void. The Boötes void is a magnifying glass for dark energy. The Boötes void, as the largest and emptiest known void, is a laboratory for this process. Its interior is one of the places in the universe where dark energy has the least competition from gravity. If dark energy behaves differently than we expect, If it varies in strength across space, if it evolves over time, if it interacts with matter in subtle ways, those effects would be amplified inside the void. The Boötes void is a magnifying glass for dark energy. This is why some cosmologists have proposed using voids as tools for measuring dark energy. The technique is straightforward in concept. You measure the shapes and sizes of voids at different distances, which correspond to different times in the history of the universe. You compare the observed void population to the predictions of models with different dark energy properties. If dark energy is a simple cosmological constant, the void population should evolve in a specific way. If dark energy is dynamical, the evolution will be different. The voids become a yardstick for measuring the expansion history of the universe. The Boötes void is too close to us, at roughly 700 million light-years, to be useful as a high redshift probe, but its very existence informs the models. If lambda CDM with a cosmological constant struggles to produce a void this large, then perhaps a model with dynamical dark energy can do better. Perhaps a slightly stronger dark energy in the local universe, or a dark energy that was stronger in the past, would accelerate void growth enough to make the Boötes void a comfortable prediction, rather than a grudging one. This is an active area of research. The answer is not yet in, but the question itself is valuable. It illustrates how a single anomalous structure can motivate new lines of inquiry and push theorists to explore parameter space they might otherwise have ignored. Let us zoom out further. Let us think about what the Boötes void tells us about the relationship between matter and space. We tend to think of space as a passive container, an empty stage on which the drama of matter plays out. Matter moves, space just sits there. But general relativity tells a different story. In Einstein's framework, space is not passive. It is dynamic. It curves in response to matter and energy. The presence of a massive object warps the geometry of space around it. This warping is what we experience as gravity. In the dense regions of the cosmic web, space is curved by the mass of galaxy clusters. The geometry is distorted. Paths of light are bent. Clocks run slightly slower. The fabric of space is deformed by the weight of trillions of stars. But inside the Boötes void, the situation is reversed. There is almost no matter. The space is nearly empty. The geometry is nearly flat. The curvature approaches zero. In a universe governed by general relativity, the Boötes void is one of the closest things to truly flat space-time that exists on a cosmic scale. It is a region where the geometry of the universe approaches the idealized, featureless, uncurved space of special relativity. In a sense, the void is what space looks like when matter has been removed. It is the background revealed. This has implications that go beyond poetry. The expansion rate of space inside a void is different from the expansion rate inside a dense region. This is a prediction of general relativity that is well established theoretically and supported by observations. The implication is that the universe does not have a single expansion rate. It has a local expansion rate that varies from place to place depending on the density of matter. Inside the Boötes void, the local expansion rate is higher than the cosmic average. Space is stretching faster there because there is less gravity to slow it down. This observation has been connected to one of the most contentious debates in modern cosmology, the Hubble tension. Different methods of measuring the expansion rate of the universe give different answers. Measurements based on the cosmic microwave background, which probe the early universe, give a value of roughly 67 kilometers per second per megaparsec. Measurements based on nearby supernovae and Cepheid variable stars, which probe the local universe, give a value of roughly 73 kilometers per second per megaparsec. The discrepancy is statistically significant and has resisted resolution for years. One proposed explanation for the Hubble tension involves the local void hypothesis. The idea is that we might live inside a large, modestly underdense region of space. If our local cosmic neighborhood has a lower than average density, then the local expansion rate would be slightly higher than the global average, which could partially account for the discrepancy. The Boötes void is not our local void. It is 700 million light-years away. But its existence demonstrates that large-scale underdensities are real, that they affect the local expansion rate, and that ignoring them can lead to systematic errors in cosmological measurements. The broader lesson is that the distribution of matter shapes the behavior of space. Voids are not just holes in the galaxy distribution. They are regions where the expansion of the universe operates differently. They are laboratories for testing general relativity on the larger scales. And the Boötes void, as the most extreme example, is the most sensitive laboratory we have. Now let us confront the deepest implication, the one that sits beneath all the technical details, the one that makes the Boötes void not just a curiosity, but a genuine challenge to intuition. We carry a deep, often unexamined assumption about the universe. We assume that matter wants to be distributed. We assume that the natural state of the cosmos is a kind of cosmic porridge, stuff spread everywhere in a roughly even layer. When we see galaxies clustered into filaments and walls, we understand that gravity pulled them together. Gravity is our friend. It is the sculptor. It makes sense. Overdensities grow. Clusters form. Beautiful luminous structures emerge. We see galaxies and we feel that the universe is working as it should. But the Boötes void inverts this perspective. It forces us to reckon with the flip side of structure formation. For every overdensity that grows, an underdensity must deepen. For every wall that thickens, a void must expand. The cosmic web is not just a story of assembly, it is equally a story of evacuation. Matter does not just gather, it flees. It drains out of enormous regions of space, leaving behind a silence so vast that a civilization living inside it might never know the rest of the universe existed. The Boötes void is a monument to this process. It is the largest known example of the universe, subtracting matter from a region of space. And its scale challenges our intuition about how efficient this subtraction can be. We accept, almost without thinking, that gravity can build a massive galaxy cluster containing trillions of solar masses of material. That seems natural. Gravity pulls things together. Of course you can make a big pile, but the Boötes void is the opposite. It is the largest known unpile. It is a region where gravity and dark energy conspire to remove almost everything, leaving behind a sphere of near-nothingness 330 million light-years across. When you frame it this way, the void becomes deeply strange, not because it violates any law, but because it reveals the universe's capacity for absence. We are comfortable with the universe's capacity for presence. Stars, galaxies, clusters, superclusters. We marvel at these constructions. But the Boötes void asks us to marvel at destruction, at removal, at the systematic, relentless, patient clearing of a volume of space so large it dwarfs everything we have ever known, or built, or imagined. There is something unsettling about that. Not in a dramatic Hollywood sense, but in the quiet, philosophical sense that arises when you realize the universe is not obligated to fill itself with things. It is perfectly content to create vast stretches of nothing. Emptiness is not an error. It is not a failure. It is a feature, a natural, inevitable consequence of the same forces that built the galaxies you admire. The universe builds, and the universe clears. And it does both on scales that make human comprehension feel like a child's toy. This is ultimately what the Boötes void teaches us. It is a lesson in humility. Not the performative humility of saying the universe is big and we are small, which is true but worn thin by repetition. A deeper humility. The humility of realizing that our intuitions about how matter should behave, how structures should look, how empty a region of space can get, are calibrated to the tiny, dense, cluttered corner of the cosmos we happen to inhabit. We live in the cosmic web. We live in the filaments and walls. We are surrounded by galaxies in every direction. Our night sky is rich with light. Our telescopes reveal a universe teeming with structure. And from this vantage point, we construct our theories. We build our models. We write our equations. We declare that we understand how the universe organizes itself. And then we point our telescopes at a patch of sky in the constellation Boötes, and we find a region of space so empty, so vast, and so barren that our models can barely accommodate it. Not because the physics is wrong, but because the universe has more room for extremity than we gave it credit for. It has more capacity for emptiness than our intuitions prepared us for. It is wilder, stranger, and more varied than the view from our particular cosmic address would suggest. The Boötes void is not terrifying because it threatens to destroy our physics. Lambda CDM will survive. The standard model will be refined, not replaced. The void is terrifying in a quieter, more lasting way. It is terrifying because it reveals the gap between what we expect and what exists. It demonstrates that the universe is not a well-behaved student following the rules we wrote for it. It is a vast, indifferent system that occasionally produces structures so extreme they sit at the bleeding edge of our predictions, daring us to explain them. And when we try to explain them, we discover that the explanation requires us to confront things we would rather not think about. The fine-tuning of initial conditions, the mysterious nature of dark energy, the limits of our statistical methods, the boundaries of the cosmological principle itself. The void does not answer our questions. It generates new ones. And each new question pulls us deeper into the machinery of the cosmos, revealing layers of complexity we had not anticipated. That is the true scale of the Boötes void, not just 330 million light years. That is the physical scale. The true scale is intellectual. It is the distance between what we thought we understood and what we actually understand. It is the gap between our model of the universe and the universe itself. And that gap, like the void, is larger than we expected. 4 decades after Kirshner, Oemler, Schechter, and Shectman published their discovery, the Boötes void remains one of the most striking features in the observable universe. It has not been explained away. It has not been reduced to a footnote. It sits in the data, massive and silent. The largest known absence in a universe defined by presence. It sends no light. It produces no signal. It offers nothing for our instruments to grab hold of. It simply refuses to contain what the rest of the universe contains. And in that refusal, it tells us more about the forces that shaped reality than 1,000 galaxy clusters ever could. Because the clusters show us what gravity can build. The Boötes void shows us what gravity cannot hold. And in the end, it is the things that slip through gravity's fingers, the matter that escapes, the light that never forms, the galaxies that were never born, that reveal the true character of the universe. The cosmos is not defined only by what it contains. It is defined equally by what it chose to leave empty. And the Boötes void is the largest, most eloquent expression of that emptiness we have ever found. It is a 330 million light-year monument to the universe's capacity for silence. And every time we look at it, it stares back, patient and vast, waiting for us to understand what the silence means. We are still listening.